In this video, I'll be discussing the 2009 AMC 10A problem number 21. Many Gothic cathedrals have windows with portions containing a ring of congruent circles that are circumscribed by a larger circle. In the figure shown, the number of smaller circles is 4. What is the ratio of the sum of the areas of the 4 smaller circles to the area of the larger circle? So, in this problem, we have 4 circles. Let's mark them. A, B, C, and D. Note that when you have tangent circles, it is always a good idea to connect the centers, because this is often the best and most useful method. Now, so connect AB, BD, CD, and AC. Let's say that let radius of circle A, circle B, circle C, circle D equals to 1. Note that in the problem it said that these circles are congruent, so they have the same radius also. Okay, now let radius of circle O, which we can call the big circle, let radius of circle O equal to R. Okay. Now, connect AB, BD, CD, AC, AD, and BC. Okay. Since AB equals to BD equals to CD equals to AC equals to 2, because they're both twice the radius of the circle, which equals to 1. So 1 times 2 equals to 2. So ABCD is a rhombus. A rhombus is a quadrilateral with 4 equal sides. Now, for a rhombus, the diagonals are going to be perpendicular. So AD perpendicular to BC. Now, we have to prove that this is a square to make it the maximized benefit for us to solve this radius of the big circle. Because the square is the most special and easiest to deal with quadrilateral. Since AO equals to BO equals to CO equals to DO equals to R minus 1. This is R and this is 1, so R minus 1. So now we can get that triangle ABO is isosceles triangle. Now, this means that similarly we can get triangle ACO, triangle CDO, triangle BDO, or isosceles triangle. Isosceles right triangle to be more specific. Now, since they are isosceles right triangle, so we can get that ABCD is a square because only in squares do the diagonals split the quadrilateral into 4 equal isosceles triangle. Now, we can find the length of R. R will equal to AO plus 1, which equals to, which equals to square root 2 plus 1. Now, you might wonder where we get the square root 2. Well, this is pretty simple. AB equals to 2, and since triangle ABO is isosceles triangle, then AO will equal to 2 over square root 2, so it's going to be square root 2. You know what? For our benefit, I can add that AO equals to AB over square root 2, which equals to square root 2. Okay. Now, so the area of the big circle equals to square root 2 plus 1, which is the radius squared pi. And then after simplification, this will be equal to 3 plus 2 square root 2 pi. Since the area of the small circle equals to 4 times 1 squared pi, because there's 4 congruent circles, which equals to 4 pi. So A small to A big equals to 4 pi over 3 plus 2 square root 2 pi. Pi cancels out. Now rationalize the denominator by timing both sides by 3 minus 2 over square root 2. The bottom part becomes the difference of square, which goes to 3 squared minus 2 squared 2 squared. So 4 times 3 minus 2 squared 2 over 3 squared which equals 9 minus 2 squared 2 squared which equals to 8. So this will equal to 4 times 3 minus 2 squared 2. And that will be C. So the key concept of this problem is that you need to know the correct helping lines to make. In this, we connected the centers of the circle, which helped us a lot because we managed to prove that ABCD is a square. Now, using some rigorous proof, we managed to prove that first ABCD is a rhombus. And then, after proving that ABO is isosceles right triangle, we managed to prove that ABCD is a square. And then the rest of the problem is relatively simple. We just have to find the length of R, which is AO plus 1. Then we can find the area of the big circle, and then the small circle, and then we found the ratio. That is how you solve this problem. Thank you for watching.